Let's welcome Eyal Leviatan from Qedma, who will present a product, an actual software product to solve some of our today's issues when doing quantum computing.
All right, thank you. My name is Eyal. I'm a researcher at Qedma. I'm going to tell you about QESEM, which is our error mitigation and error suppression software, which promises reliable and accurate results for large-scale quantum circuits. So let's start with a does statement. Quantum computers today, because of errors, are not useful. Even if gate operations have a small infidelity, that noise accumulates through the circuit, and for deep enough circuits, the signal is corrupted. So if you're only interested in shallow circuits, you may be able to get away with it with low volume to get reasonable accuracy. But if you want to go to high volume into quantum advantage area, you get very low accurate results because of the infidelity. Now, one possibility, maybe in the future, is error correction. The problem that today we don't have enough good qubits to facilitate error correction, or the ratio of physical to logical qubits also brings out logical qubits that do have infidelity in them. But in this plot on the right, I like to view it as kind of a resource plot. If we don't have enough physical qubits for error correction, maybe we have enough QPU time for error mitigation. And so, say you have some maximal QPU time that you're willing to use, some error mitigation techniques will be beyond that and will be out of your reach. But we argue that QESEM is an efficient one, which you can still use to get good results. And I will point out that in the future, we expect actually error correction and error mitigation to combine together in a way that you will be able to optimize in this resource plot how many qubits you're willing to use and how much time you're willing to spend. So you're not going to have to work either on this end or on this end. You can work somewhere in the middle. All right, so one more point about error mitigation before I show you some demonstrations. And we like to call this circuit volume boost. So say you need some accuracy on your simulation. Let's say 95% accuracy. So that limits the size of the circuit that you can run, right? So if the circuit is too deep, you're not going to get the accuracy you want. So if you need some accuracy, that puts a limit on the circuit depth given device with some infidelity for the gates. If you're willing to spend some more time on mitigation, and that more time is this X parameter up here. So say you're willing to spend 10 times as many shots, then that would give you this blue curve up here, which already buys you about a factor of 20 in the volume of the circuit. So if you're willing to spend some more time, you're going to be able to go to very much deeper circuits per your desired accuracy. And as you need more and more accurate results, this actually blows up. So you can get really high factors here. Okay, so this is didn't move yet? Okay, so this is the workflow for our product. I'm not going to go through it in detail because this is a short talk, but I will say that in titles. So there's an input circuit given by the user. We first do some QPU characterization in order to inform our transpilation. So we do noise-aware transpilation. It includes choosing the right qubits, but not only that. It also includes changing some gates into other gates, while keeping, of course, the ideal circuit intact. Then we perform some error suppression, calibration of required gates, etc. Then there's a circuit characterization, which really characterizes the operations chosen for that specific circuit, and that characterization informs the mitigation part. In the mitigation part, we execute a lot of different circuits, and out of all these noisy outcomes, we can reconstruct the ideal outcome for the input circuit. And there are some key innovations that we put in. I'm not going to even discuss all of them, but I will point out a few. One of them is the active volume identification. So you may know that if you're interested in some observable at the end of the circuit, maybe it acts only on a few qubits, but throughout the circuit, there's a light cone of qubits that actually affect the outcome of that observable. Now, naively, you would want to correct all the errors in the circuit, but actually, if you're only interested in that observable, you only have to correct the errors within the light cone that affects it. And so identifying the correct light cone can really make the error mitigation more efficient, since you can essentially not deal with errors that you know have no effect. And that's an important point. One other thing that I want to point out is the drift mitigation. So this mitigation method is based on characterization. And the important question in characterization-based mitigation methods is the noise model correct, or for how long is it correct? So our product actually does a deal with drifts in the machine if the noise model changes in time. We do have methods to take care of that. So that's the drift mitigation part. So the result really is drift robust to some extent, of course. You can't be perfect. Right, so let me go forward. So this is a bit of a technical thing. I don't want to go over all of it, but it shows how to set up a QESEM job through the QESEM function. What I do want to show you is the mouse clear? Yeah, perfect. So you have to define your circuit of interest, the observables you want to measure, and some precision that you want to get on that observable. And then you can either just start the job that's down here, we'll get there in a moment, or you can start with you can start with a time estimation. So the time estimation will let you know how many shots and how much QPU time is required to actually reach the precision you wanted on the observable you wanted on that circuit. And there are two options for this, the analytical one and the empirical one, which is commented out here. The empirical one actually does execute some circuits on the device, but it actually gives a correct estimation. The analytical one is an intelligent guess, but a guess eventually. So then you can get this time estimation. It will tell you something like this: 3,600 seconds of QPU time, maybe. Then you can run the job, and you would get eventually the expectation values and the error bars of the observables that you input. You also get some other numbers if you want, but let's not focus on them. So here's a recent demonstration that we did. This is on IBM's Marrakesh device, a Heron device. Here we do two-dimensional Ising Hamiltonian simulation, like a time evolution. This has 103 qubits, actually, not 100. 100 qubits, more or less. And this down here is what the circuit looks like. It's interleaving fractional RZZ gates that implement the ZZ interaction, and single qubit gates Rx and RZ that implement the magnetic fields in the X and Z direction. And you can already notice that the parameters we put here are essentially generic. So the RZZ is a fractional gate. At this parameter, it's not Clifford. And we do have both fields, so this is kind of a generic Hamiltonian. And importantly, it has a significant light cone. So you can see that here. Say we're interested in a single Z on one of the qubits at the end, then this is for the 8th step, I believe. So in the base of the light cone at time 0, that would involve 54 qubits out of the device. And up here you have the results. So on the y-axis, we plot the average magnetization. That's averaging all the Z expectation values of all the sites. The dashed gray curve is the ideal outcome calculated with tensor network methods. So PEPs in this instance. The red dots are the noisy values, absent, I wouldn't say any error mitigation, but the main part. So this is already Pauli twirled, which in some sense does some mitigation or suppression, if you would like to think about it that way. And clearly the red points do not recover the correct signal, which is like obvious. But then the blue points are the outcome of our product, and you can see that they come with statistical error bars due to the finite number of shots used to generate them, but they do recover the ideal outcome up to these error bars. Then on the right, if you're interested, you can see other observables like the ZZ correlations or ZZZ or whatever, higher weight stuff.
How did you, for this large system, simulate the classically, I mean, you had the classical simulation to know the ideal solution?
Right, so we did that with tensor networks. So IBM's device is barely 2D, so you can use belief propagation. And to step 8, that's actually still possible at relatively low bond dimension, and it's converged. But in 2 slides, I will show you that that's not too far behind the place where things already diverge at pretty large bond dimension. Anything else here? Right, so zooming in on step 5, which I will point out as this step. I'm showing here all the various single site Z's. So all the various qubits here, 103 qubits, they're Z's. Again, the colors are the same, but maybe more interesting is the histogram down here, which shows again these, but aggregated, where on the x-axis we show the z-score, the deviation from the mitigation of the mitigated from the ideal, normalized by the mitigation error bar. And you can see that really the blue curve here, which is the output of our mitigation, it's normally distributed as it's supposed to be. So the method actually does produce up to a statistical error bar the correct result. So you can see that it's more or less within -3 to 3 sigmas. It's peaked around 0. It has all the right characteristics. Whereas Z&E really misses here. So it's peaked in the wrong place. It's too wide. It doesn't actually do the correct thing. But it might be correct for certain observables, like here, the Z&E is fine, but overall it's not doing the right thing. Right, and this is what I said before. So this is the same model. These are all classical simulations. The black and the gray ones are essentially Pauli paths done on one of Riken's supercomputers. You can see that they already diverge from the PEPS solution at about, say, 6 or 7 time steps, 6 or 5. Then the PEPs actually agree between bond dimension 128 and 256 up to, say, the 9th time step. And we didn't check further. I'm guessing that the bond dimension 512 would agree over with the 10 time step with one of them, but things start to diverge away. So if we are able, so we're not that far behind. If we're able to just push a couple of more time steps forward with this, maybe slightly better in fidelity, slightly better transpilation, slightly more efficient mitigation, we're going to be at the regime where we don't have really reliable classical simulations to back us up. And then we need to for the mitigation to be reliable. So we're not going to be able to use Z&E anymore because it's not clear that it's trustworthy. This is a different demonstration. Here we took a VQE circuit already optimized with the right parameters. The optimization was done classically. So we're just simulating the ground state and computing the energy. And here we used a nice feature that we have that parallelizes so on the device. So the circuit itself is only 8 qubits, but the device is much larger. And our parallelizing feature, it kind of chooses the first patch. Let's say it's this one. And then it asks, well, what's the second best patch? Is it more helpful to run on it simultaneously or just add more shots to the first patch? And so it collects patches on the device in that way until it says, okay, now adding another patch is not worth it. So here we ended up with 9 patches. You can see them colored on the left. And these are the 9 patches, the mitigation result in blue, the noisy in red. So you can see all of them are reproducing the ideal, which is the dashed gray line, up to statistical error bars. And this over here on the right, but not the Z&E, is the inverse variance weight of all 9 patches. So this is the final result of this experiment, also reproducing very nicely the correct result, whereas the Z&E slightly misses. So these are just a bunch of users that have already used our software. If you see here anyone you're familiar with, you can discuss with them, but let me skip that. And I want to tell you about 2 final things before I finish, which are kind of our outlook right now. So one of them is to combine QPU with HPC computing. And that's a collaboration we have with Riken. So essentially what we do is, say you wanted to time evolve some state to some capital T, you can actually split that up and Heisenberg evolve the observable you're interested in at the end to some tau, and Schrodinger evolved the state to t as long as t plus tau is this capital T that you were interested in. The blue part, the observable part, is done classically with the matrix product operator methods, and then whatever operator you ended up with, however complicated, with however many measurement bases required, is just the input along with the initial state to the quantum circuit, to our QESEM job. And so here on the left, on the right, we have a demonstration, again, on one of IBM's devices. This is 75 qubits in 1D, so you can see the snake snaking around here. And so the down below, again, the red are the noisy, ideally are in gray. It's hard to see because the blue ones essentially cover them. The blue ones are the mitigated. But I've shaded the region on the left where quantum, where the quantum computer could take us without the help of the classical computer. And with this method, we were actually able to go way beyond that, up to 25. So in this entire thing, tau, the classical part, is fixed to 10. And we start, so 12 here is 2 steps on the quantum computer. 25 is 15 steps on the quantum computer. And so this is nice. This is kind of the HPC helping the QPU. What we would really like to do is have it the other way around, right? So you would use the HPC to evolve the observable as far as possible when the next step is already not feasible, and then go to the quantum computer and add some steps using that. So we're working on that now. The second thing, am I out of time? Okay. This is almost the last slide. So let's focus on the left part. So you've already seen this plot. I showed it to you with the gray line and the blue line. That's the E error mitigation and the raw. This is, again, the volume boost. And I just wanted to point out that error correction would offer a different horizontal line, right? Improving stuff, maybe improving very much, maybe not that much, depending on the error correcting code and the logical infidelity. But then you can just apply logical error mitigation on the logical qubits and get, again, this volume boost. This is the green line. And actually, there's something smarter that we're working on, which we call Salem syndrome-aware logical error mitigation, to appear on arXiv soon, which produces the orange line, which is even better, offering an even larger volume boost by combining in a smart way, not the naive way, error correction and error mitigation. Let me skip this because of time. So let me just point out that we are offering soon 4 months of free access through the Qiskit function. If you're interested in testing our product, you can contact us. The email is down here and all over the slides. And take part in this and see if the product meets your needs. And even without this freemium, you're welcome to always contact us and see if we can collaborate or initiate anything. And that's it.